It says it's recording. Make this larger. Okay. We have this last little section, 4.5, functions of matrices. There we go. All right. So that's okay. All right. So functions of matrices. This is going to be the Caley-Hamilton theorem. So first of all, let's make sure we all know that given an n by n, so a square matrix A, if we're going to let a to the power of 1 be a squared would be a times a cubed would be a squared times a. So if you're wanting a to any power, you just take the power right smaller than it and multiply it times a. And then keep in mind a to the 0 will be the identity matrix, and it'll match the same square size, an n by n. So a to the 0 will be just identity matrix, which is ones down the diagonal, zeros everywhere else. So the Caley-Hamilton theorem says that if A is a square matrix with characteristic polynomial P, we plug A into that characteristic polynomial, it's going to equal 0. So we get that characteristic polynomial by doing lambda times the identity matrix minus A, and then finding the determinant of that. That'll give us the characteristic polynomial. And then now it's saying if we plug A in there into that characteristic polynomial, we're going to get 0. So, and that's going to allow us to find more complicated versions, like we can find a to the 4th without having to multiply a times a times a times a. So that's where it's going to be helpful. All right, so for each of these matrices, we'll find the characteristic polynomial first, and then we'll use the Caley-Hamilton theorem to find a to the 4th, and then also a inverse. So let's do first example. All right, so we're going to start with lambda times the identity matrix minus a. So that'll be a lambda minus -4, 0 minus 2, 0 minus -1, and then lambda minus 1. And so first thing they want us to find is the characteristic polynomial. Remember, the characteristic polynomial is the determinant of this matrix here. That's what gives us the characteristic polynomial. So the determinant would be lambda plus 4 times lambda minus 1 minus, we multiply down the diagonal, minus -2 times the -1. And so that'll give me a lambda squared minus 1 lambda plus 4 lambda, so a plus 3 lambda, minus 4 plus 2, we have minus 2. So there's your characteristic polynomial. This is the characteristic polynomial for this matrix A. Now, what they're saying is if I plug the matrix A into this polynomial, it'll equal 0. That's what the Caley-Hamilton theorem states. So what that does for us is it's going to allow us to find a to the 4th much easier and a inverse much easier. All right, so since your characteristic polynomial for this guy is lambda squared plus 3 lambda minus 2, if I now do E of A, Caley-Hamilton theorem says if I plug in A into this guy, it's going to equal 0. So A squared plus 3 times A minus 2 by Caley-Hamilton, this guy is equal to 0. Yeah. All right, so what does that mean? Well, since it's equal to 0, then I can isolate my a squared. That would mean a squared is equal to, add the 2. Now keep in mind, we're talking about matrices here. So 2, what does it mean to just be 2? You're adding and subtracting matrices from 2 you can't do that. You need a matrix. So if it's just a constant, I'm going to add times the identity matrix. That's how you're going to be able to add 2 to anything or subtract anything. So, so I added the 2 times I. Now, so we're going to insert an I into here because now we're talking about matrices, right? So adding the 2 i's and then subtracting 3a. So now I know a squared is 2 times the identity matrix minus 3a. It allows you to quickly find a squared instead of multiplying it through. But we want a to the 4th, right? And certainly you could do a times a times a times a, but here's just an alternative method that makes it easier. All right, so if I want a cubed, then what I would do is take this equation here, and if I multiply both sides of the equation by a, then this left-hand side will be a cubed. Now, so I'm going to take and multiply times a and multiply times a, so that you end up with a cubed equals 2 times a times I. Well, a times I is just a, so this becomes 2 times a, and then minus a times 3 times a would be 3a squared. Now, all right, but I have something for a squared. A squared we had just found right here was 2i minus 3a. So I'm going to substitute 2i minus 3a into this a squared here, since a squared was equal to 2i minus 3a. So that means I would have a cubed is equal to 2a minus 3 times, and I'm replacing it with 2i minus 3a. Then I'm going to simplify this so that a cubed is equal to, this would be 2a minus 6i and then plus 9a. So a 2a plus 9a will give me 11a minus 6i. So now I've got a cubed. If that's what they were asking me for, I could just simply plug in the matrix A and then plug in the identity matrix there. But we want a to the 4th. You know? And so for a to the 4th, you're going to multiply both sides of the equation by a, so that you get a to the 4th is equal to 11a squared minus 6 times a times the identity. A times the identity matrix is just a, so you just end up with 6a. But I know what a squared is. Now, we found it right here. So I'm going to substitute that. 11 times, and again, it's a squared right here was equal to 2i minus 3a. So I'll put that in, 2i minus 3a, and then minus 6a still. Distributing that 11 would give me 22i minus 33a, and then subtract another 6a, so that we get a minus 39a. And now, super easy to plug this in, right? So that we get, so now, a to the 4th would be 22 times the identity matrix. We need a 2 by 2 since a is a 2 by 2. 1, 0, 0, 1 minus 39 times matrix A, which was negative 4, 2, negative 1, 1. And then we'll distribute that. Distribute the 22. So you get 22, 0, 0, 22 minus 39 times negative 4 would be negative 156. 39 times 2 gives you 78. This would be a negative 39 and a positive 39. So that when you do 22 minus negative 156, it'll give you 178. 0 minus 78 gives you negative 78. 0 minus negative 39 will give you a positive 39. And then 22 minus 39 will give you negative 17. So that's what a to the fourth is equal to. Yeah, not too bad. All right, so they wanted us to find a to the fourth. So that's a to the fourth using Caley-Hamilton. Right. Now, what we'll do is they also want us to find a inverse. All right, so how are we going to find a inverse? For a inverse, and again, they want us to use Caley-Hamilton. I should say use Caley-Hamilton, so don't just go flipping things and find the inverse the way you know it. All right, so here's what I know. I had my characteristic polynomial was that a squared, well, remember we had plus 3a minus 2i was equal to 0. That was the Caley-Hamilton theorem, said that plugging a into your characteristic polynomial is equal to 0. And then we isolated a squared. A squared was equal to 2i minus 3a. So now I want a inverse, right? So I'm going to take this and multiply both sides of this equation by a inverse, so that you'll get a inverse times a squared and a inverse times 2i minus 3a. All right, so what do we got here? Keep in mind, a squared is a times a, and also remember that when you multiply a times a inverse, it'll equal the same thing as a inverse times a, which is the identity matrix. Right? So this guy is like, I guess I'll write it out. It's like a inverse times a times a. So that this ends up being the identity matrix, and then times a, so you just end up with a. And this guy is 2 times a inverse times I, and minus 3 times a inverse times a. So that, you got I here. A inverse times I is just a inverse. And then a inverse times a is I, the identity matrix. So you end up with a is equal to 2 times a inverse minus 3i. Well, and what I want to solve for, I want a inverse by itself. So how about if we add 3i over here? So I've got a plus 3i is equal to 2 times a inverse. Dividing both sides by 2 gives me a 1/2 times a plus 3 times the identity matrix will give me a inverse. Beautiful. So now that means a inverse is 1/2 of, I smooshied it. A was -4, 2, -1, 1. 3 times the identity matrix will be 3, 0, 0, 3. Add these inside here first. -4 plus 3 will give you -1. 2 plus 0, -1 plus 0, and 1 plus 3. I'm fine with you leaving your answer like that. Or you could have distributed the 1/2 inside there, and you would have had -1/2, +1, -1/2, and a +2. So either one of those answers is fine. I would just leave it out like that. All right. Let's do another example. Let's do a 3 by 3. So we've got a is equal to All right, so there's your matrix A. To find the characteristic polynomial, first you need lambda times the identity matrix minus A, which will be lambda minus 1. Lambda minus 1. 0 minus 0. 0 minus negative 2. 0 minus 0. Lambda minus 0. 0 minus 3. 0 minus negative 2. 0 minus 1. And lambda minus 0. All right. So there's your lambda minus A matrix. The characteristic polynomial, we call it P of lambda, is the determinant of this matrix. We got a 0 here already, so that's nice. I'll only have 2 of these guys, so I'll just do it from here. Lambda minus 1 times, cover that up, and I'm covering up that first line here. Determinant of that guy would be lambda squared minus positive 3. We technically have a minus 0 times blah blah, right? Who cares? Plus 2 times this guy and that guy. Determinant of that little minor is a 0 minus 2 lambda. All right, so then we will multiply those and you get what? Lambda cubed minus lambda squared minus 3 lambda plus 3, and then a minus 4 lambda, so that your characteristic polynomial is lambda cubed minus lambda squared minus 7 lambda plus 3. That's your characteristic polynomial. Characteristic polynomial. So that was part A. Part B then says use the Caley-Hamilton theorem to find a to the fourth and a inverse. So by Caley-Hamilton, P of A would be 0. Well, that means that I would have, plugging in an A into all these lambdas, A cubed minus A squared minus 7A plus 3 is equal to 0. So what we'll do is let's isolate A cubed. A cubed would equal A squared plus 7A minus 3. Let's add in a, we're talking about matrices here now, so I'll add in an I there. Constant is times the identity matrix. Okay. All right, so now that means I can now do a to the fourth. So a to the fourth would be, I would multiply a times both sides of the equation. So a to the fourth would be a cubed plus 7a squared minus 3 times a times the identity matrix, which just leaves me with an a. And what do I have? Well, the only thing I know is a cubed right now. So this a cubed, I'll replace it with the right-hand side of this whole guy, right? So that this ends up equaling a squared plus 7a minus 3i. And then I still have a plus 7a squared minus 3a. Cleaning that up, combining like terms, I would have a squared plus 7a squared would give me 8a squared. 7a minus 3a will give me a plus 4a, and then a minus 3i. All right, so not as nice as the last one because they're not all in terms of A's and I's. So we do need A squared, right, in order to finish this off. So I do need A squared. And to find A squared, you're just going to take A. I apologize for the slamming doors. I don't know if that came through the audio. And -2, 1, 0. All right, so we multiply these. We got 1 plus 0 plus 4. Give me a 5. 0 plus 0 plus -2. -2 plus 0 plus 0. 0 plus 0 plus -6. 0 plus 0 plus 3. 0 plus 0 plus 0. -2 plus 0 plus 0. 0 plus 0 plus 0. And then 4 plus 3 plus 0. Nice. All right, so there's A squared. Now we have everything we need to plug in, right? I've got, this is what I'm going to plug into A squared. My A was my original matrix A, and then I is that identity matrix, a 3 by 3 this time. So A to the 4th will equal, so A to the 4th will equal 8 times the A squared we just found, plus 4 times A, and A was 1, 0, -2, 0, 0, 3, and -2, 1, 0. And then we have -3 times the identity matrix. So it'll be a 3 by 3 identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, let's clean it up. Actually, you guys can do that, right? Your final answer ends up being 41, -16, -24, -48, +21, 12, -24, 4, and 53. So A to the 4th. Which really, that was much simpler than having to multiply a 3 by 3 times itself 4 times. I know we still have to find A squared. Sometimes that happens. But it really does make things easier sometimes. All right, how about for A inverse? I'm going to take that A cubed, right? And it was equal to what? A squared, and I'm going to leave room, plus 7A and minus 3I. And I'm going to multiply everything by A inverse. So times A inverse, times A inverse, times A inverse. It's okay for me to pull that constant in front of it, no big deal. And then A inverse. I am multiplying A inverse on the left of every single one of these matrices, though. The only thing I'm pulling out front is the constant. So this is A inverse times A cubed will leave you with A squared, because one of those A's with the A inverse turns into identity matrix. One of these A's with A inverse turns into the identity matrix, so that's just an A to the power of 1. This is a 7 times the identity matrix, since A inverse times A is identity matrix, and then minus 3 times A inverse times A identity matrix is A inverse. And what we want is A inverse, so I want to isolate this term here. So I think I'll, just so that it's positive, I'll bring it over to the left-hand side, adding it so that I've got 3A inverse and subtracting the A squared on both sides. So equals A plus 7I minus A squared. And that means A inverse is equal to 1/3 of A plus 7I minus A squared. And now we can plug things in. All right, so A inverse is equal to 1/3 of matrix A, which was 1, 0, -2, 0, 0, 3, and -2, 1, 0, plus 7 times the identity matrix, a 3 by 3, and then minus A squared, and we already found A squared in the previous step. That was a 5, -2, -2, and -6, 3, 0, and then -2, 0, 7. So that you've got 1/3 times 3, 2, 0, 6, 4, 3, 0, 1, 0. And I'm fine with you leaving that 1/3 factored out. If you wanted to distribute it in, that's fine too. Would have been what? 1, 2/3, 0, 2, 4/3, 1, 0, 1/3, 0. So that's fine too. That looks nice, pretty, clean. No, not too shabby. All right, that's it for this lesson. So there we go. There we go. All right, I hope you guys have a good day and come see me in office hours. If you have any questions, okay? Bye.